Today's topic is Fick's second law of diffusion. Yesterday one video was posted which was on Fick's first law of diffusion, and here I am talking about Fick's second law of diffusion. By using the first law of diffusion, the mathematical expression for first law of diffusion was what? The first one, this one. J is equal to minus d del C del x. Del C del x. J is equal to minus d del C del x. J is what? J is diffusion flux. D is diffusion coefficient or diffusivity. C is the concentration gradient and x is the spatial coordinate. So this equation has been written for only one-dimensional case. You can use for two-dimensional as well as for three-dimensional cases. Okay, there will be little change in the equation. Okay, for simplicity I have written here only the one-dimensional form. And now I am talking about Fick's second law of diffusion. That means what? This law is used only for time-dependent problem on diffusion. The first one, Fick's first law of diffusion, that is time independent, means that is used for steady state diffusion condition. Okay, and here in the second case means when we are talking about Fick's second law of diffusion, here the problem is time dependent. Here the concentration gradient does not remain fixed over time. With time it is changing. If with time concentration gradient changes, then in that case you must have to use the second law, Fick's second law of diffusion. Okay, and derivation of the second law is made using the first law of diffusion. But one more thing you have to combine with the first law, that is conservation of principle of mass. So combining the first law of diffusion, first law means I am talking about Fick's first law of diffusion and conservation of mass. If you combine these two principles, then you will get the second law, and you can see that the second law is this one. The mathematical expression for this the second law is this one, del C del T. Here small t denotes time. C is nothing but concentration gradient as in the previous one. Okay, here D is again diffusivity or the coefficient diffusion coefficient. Okay, and x is spatial coordinate. So D is diffusivity, and one more thing, here there is no negative sign. Okay, here it is positive and here it was negative sign. Okay, so this equation can be solved for different problems. If in your problem, okay, say the geometry is simple. Okay, if geometry is simple, then analytical solution for the second equation is available. You can easily analytically solve the second equation for simple geometries. But if in your problem the geometry is not simple, then you have to go for numerical methods such as finite difference techniques are there, finite volume techniques are there, again finite element methods are there. So different methods are available. Okay, finite differencing method, finite volume method, and finite element method. More methods are also available. Okay, so many methods are available, and this equation is not a complicated equation. Okay, easily you can solve numerically. Depending upon the problem, you need to choose the numerical schemes. Okay, so anyway, in practical problems, in so many practical problems, whether the field is chemistry, whether the field is biology, or whether the field is physics, or chemical engineering, or material science, or metallurgical engineering, okay, everywhere you will find time-dependent diffusion problem. Means concentration, if a concentration gradient is changing over time, then in that case you need to use the second one. Means Fick's second law of diffusion. Okay, and the second law has also been validated experimentally by using the method of spectroscopy. Different methods are available to verify the second equation. Yes, experimentally the second equation was validated. Okay, so there is no problem with the equation. Okay, so this was all about one more thing. In such problems, pressure gradient is assumed to be zero. There is no pressure gradient. If pressure gradient exists, then there will be bulk flow. Along with diffusion, there will be bulk flow. If pressure gradient exists, and if pressure gradient is zero, means pressure gradient does not exist. A meaning of which is pressure gradient is zero, so only diffusion will take place. As long as there is concentration gradient, as long as there is non-zero concentration gradient. Okay. If concentration gradient is zero, if and along with this pressure gradient is also zero, then in that case there will be no diffusion, there will be no bulk flow. Okay. So here in this problem, pressure gradient has been assumed to be zero. So there is no bulk flow, only diffusion is present due to the presence of diffusion gradient. Okay. Rate of change of concentration with respect to spatial coordinate, that is called diffusion gradient. And here in this case, only one dimensional problem has been shown. Okay. But the same thing can be used for two-dimensional as well as three-dimensional with a little change in the equation. Okay, so this was all about Fick's second law of diffusion. Okay, so this is the end of this video. Thank you for watching this video.